Kinetics is concerned with the rate of chemical reactions. So the first thing we want to do is talk about how we define a rate, how we characterize how fast a reaction is occurring. So we know for every reaction, it's reactants becoming products. And so we know that as a reaction occurs, the amounts of reactants present should be decreasing, the amount of products increases, right? Reactants are becoming products. You're changing what is present over the course of the reaction. So for a fast reaction, the amounts should change faster, right? Really slow reactions, the amounts don't change. In really fast reactions, the amounts are changing really quickly. You're losing reactants very rapidly, and you're gaining products very rapidly. In order to, we could monitor amount using like moles or anything like that, but any sort of amount would work, mass, but we're going to use concentration. This makes it a bit, you can compare different systems more cleanly, right? Because concentration just describes, you could have different solutions of different sizes with similar concentrations. In order to describe concentration, we are going to use square brackets around a chemical formula to indicate molarity. So the first idea, we're going to be using molarity as concentration basically from here on out. So everything through kinetics and moving forward, we're still going to be talking about concentration, and molarity will be our desired concentration of choice. So whenever we see a molecular formula that has square brackets, that implies it is the molarity of whatever's inside. So NaCl as a molecular formula inside square brackets implies that that quantity is the molarity of NaCl. We're going to use that similar to like a variable in equations. Okay, so if you have the reaction rate, it's going to be the change in concentration over time. So reaction rate should always have units of concentration per time. So because our concentration, molarity per time. It can be seconds, hours, days, years, weeks, whatever, milliseconds, nanoseconds, whatever makes the most sense for that reaction that you're looking at. So for example, if I want to look at this reaction, N2 plus 3H2 gives me NH2 and H3. I want to characterize the rate of creation of NH3. How rapidly is NH3 being created? And so I want change. So this delta here is always going to imply change. Remember, the square brackets are the molarity of that compound, so molarity of ammonia, divided by change in time, so delta T. And so in this case, these deltas, that just means differences, so it means subtraction. You will note over here, I have put these basically subscript of times. So you'll note the change in time is T1 to T2. And then when we use these brackets to represent molarity of a compound, we use a subscript of a time afterwards to denote the time that I'm looking at that molarity of. So this first thing would read, this is the molarity of ammonia at time 2, or at the second time. So this is similar to this is a function, the molarity is changing with time, and so it's the function at time 2. That is the input variable that you would go in because your molarity is going to depend on time, and it's going to be changing with time. This is a reaction that we're looking at over time. So if we actually look at some actual data, say you perform this experiment and you looked at your concentration of ammonia over time, it's a product, so the concentration is increasing on our graph, which is what we would hope because we're making products. That's good. Our reaction is successful. It has observable kinetics. It's not, very, 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 very slow. So when we want to actually calculate out these rates, what we would do is we would pick, say, 2 points. So we started at time equals 0 seconds and time equals 60 seconds. So we just did this over 4 minutes. 60, 60, we're looking like that. So if we want to do the delta NH3, what we do is we take the 109, which is the concentration at the higher time, right? It's not necessarily that T2 that's right there, just indicates what time it is that you're measuring out or specifying the concentration at. What the concentration at time 2, which is the 60-second time point, is 1.09, and then at the time 1 time point, it is 0.75. and then we divide by the 60 seconds to get us the molar per second. And so what we can see is that molar per second basically is giving us the slope. You'll note this is the slope formula that we're looking at here, rise over run. Rise is the change in concentration. Run would be the change in time. And so we can see that you're getting 0.0057 molar per second. So that's actually pretty good growth. That's pretty high. And so we're doing pretty well. If we look at, say, a different set of points, because we just ran this experiment over time, we could plug in their numbers. You will note now 109 is the first time point, so that's why it's showing up right here. And then we can take that out, and we can see that we get 0.003. That is a smaller value than before, and so the rate has slowed down, indicative of the fact that the slope is more shallow between the second and third point. And this trend continues. We can see that they kind of shallow out and then shallow. So we can see that over time, the rate of a reaction varies. It starts out, in this case, it's going pretty quickly, and then it starts to slow down. That's actually a standard or expected behavior, that reactions tend to slow down over time. And so this is great. We can calculate these average rates, but we're still kind of leaving something to be lacking. We want to be able to calculate like this, but we want to also be able to move forward. And so that's why we can calculate what's called an instantaneous rate. Instead of looking at a slope between 2 points, so the blue line on this is showing, say, the change in concentration over time. So now it's decreasing because, say, I'm looking at a reactant species. So say I'm decreasing my concentration over time. Instead of picking, what I was doing before was, say, picking a point here and a point here and calculating out the slope between those 2 points. Obviously, that's not slope, but not secant. But, that's the idea, right? We picked 2 points. And so you can see that depending on where you pick those 2 points, it's really going to vary. And ideally, what we would like to get is, instead of some sort of averaged rate over time, I want to know how fast is the reaction going at this specific time. And so what we could say is, well, at this time, the rate of the reaction is still the slope of a line, but it's the slope of what's called the tangent line. It basically is showing how quickly is the graph changing, or is my line changing, at this particular point. So here at the start, the slope is steep, right? The blue curve looks steep, and the orange dashed line that meets it right there is showing that would be if it was a straight line that matched with that part of the blue curve, that's what the slope would be. Further out, it does become shallower. So an instantaneous rates can happen at any time. A lot of time we define what's called the initial rate. This is the rate right when we mix our reactants, right when we start the reaction. Basically, this is useful for experiments because you know exactly what the conditions are because you mixed them in that initial system. And so you can have good control over what the conditions are. And that way you can directly relate initial rate, how quickly is the reaction happening right now, to this idea of, what are the conditions? What are my concentrations? What's the temperature? All those things we've talked about previously that can potentially control reaction rate. I do want to put a little disclaimer. You may recognize some of the math that's going on here. There's a lot of calculus underpinning this. You do not need calculus for this. You don't need pre-calculus. We're going to not worry about it. We're just going to say what these things are. You don't need to be able to obtain instantaneous rates from a graph. So no worries if you're recognizing some things that are giving you some concern. No calculus here. There is a lot of calculus here. We're just not going to be doing any of it. Everything that underlies this. We're just going to get the outcome of some calculus processing. All right, another video down. No participation questions here, but I think we're just warming up. Couple of videos, still got some more to go. I'll see you in the next one. See if we find any more participation questions. See you there.